Do you want to know how this turns into this? In this video, I'm going to be talking about the metamorphism of mafic igneous rocks like basalt and gabbro. First things first, metamorphosed mafic rocks are called metabasites, and the protoliths, or the original rock to these metamorphosed rocks, are basalt or gabbro, like I just mentioned. And these basalt or gabbro protoliths contain Plagioclase feldspar, which is a series of compositions from sodium-rich Plagioclase to calcium-rich Plagioclase, and we'll talk about how that composition changes throughout different metamorphic facies as these rocks are metamorphosed. And then pyroxene, which is also a range of different compositions that typically contain some amounts of calcium, magnesium, and iron in different relative ratios. And then also olivine, which is a ferromagnesian silicate. So we can see in these thin sections over here that Plagioclase can make up the kind of fine grain matrix of a basalt, or can contribute to the fine grain matrix as these tiny little tabular plagioclase crystals, but it can also be larger phenocryst type of clasts in the finer grain matrix. But in any case, the plagioclase does have a tabular structure in the basalts and gabbros that are the protoliths to the metamorphosed material that can contain plagioclase, but as you'll see, it's not tabular anymore. So texture is a very important thing here. And then we can see pyroxenes and olivines also are like the blocky, colorful stuff in these plagioclase-rich basalts over here. And during metamorphism, with increasing temperature and pressure, the mineral assemblage changes, and these changes are different for each metamorphic facies. So these regions over here in this graph are metamorphic facies that we'll talk about, like the Greenschist Facies, the Amphibolite Facies, etc. And so we'll talk about how basalt and gabbro can change their mineral assemblage and their textures in each one of these metamorphic facies, and then what rock type that would be called in each one of the facies, which is relatively easy because the facies are named after many of these rocks. First, we have the Greenschist Facies, because we're going to skip the real low temp facies for now, like the Zeolite and PP Facies, but we'll talk about those later. The reason we start with the Greenschist is because typically, and like, you know, the typical regional metamorphosed environment, starting at the Greenschist and getting more high temp and pressure is more common than with really low temperature. But we'll talk about what can happen in low temperature zeolite type facies later. So for the Greenschist facies, surprise, surprise, greenschist is the rock that forms in this facies from a basalt or gabbro protolith. And when the rock is foliated, it is called greenschist. And when it's not foliated, it's called greenstone. I put question marks by these because I'd really have to look at them more closely to see if they're foliated or not, because this greenstone over here is kind of fine grained, and the green schist over here is more platy, but I can't tell if it's really foliated. I'd have to kind of look at it and make sure. But anyway, if they're foliated, it's green schist. And if it's not, it's greenstone. It has a green color because of minerals like actinolite, epidote, and or chlorite. Actinolite is really the big one that kind of mainly defines this facies. If actinolite's present, it defines that you're in the greenschist facies. But epidote is also common in green and hand sample and plain polarized light, as you can see. And chlorite, which kind of can look multiple ways under thin section. Over here to the right, we have one in cross polarized light that's kind of like a black and white sheen to it, but over here to the left we have one again in cross polarized light that's kind of like a brownish black sheen to it, whereas the plain polarized over here is greenish, and the plain polarized of the one over here, I don't have it up, but it's more clearish. So I think from what I found online, and I'll put all the resources down in the description below, although some of these, like this one over here, is my own picture that I took when I was taking this class. But from what I found, it seems like chlorite can kind of vary in its appearance under thin section. And that's kind of unfortunately the trend for a lot of minerals. A lot of minerals vary, especially mineral groups, which we'll talk about later. Because like Amphibole is a group of minerals. Pyroxene is a group of minerals that vary widely in composition and therefore can vary in their colors and whatnot under thin section. But the general habit of actinolite and chlorite is kind of platy. Epidote is a little bit more blocky from what I've seen, but we'll show more examples as we go. Plagioclase in this facies, in the Greenschist facies, is typically pure albite. So that's the sodium side of plagioclase. Remember, it goes from sodium to calcium plage, and sodium plage is called albite and calcium plage is anorthite. And we'll talk about both of those kinds of plagioclase in this video. But at low pressure, more calcic plagioclase might be present in the Greenschist facies. And possible accessory minerals in this facies could be quartz due to the formation of epidote and chlorite, which release silica, because typically the minerals assemblage of basalt and gabbros don't have a lot of original, quartz or pure quartz in them, but they are silicate minerals. So they have silica in their composition. And so when they transform into different minerals, it could release some of that silica to form quartz as an accessory mineral alongside things like epidote and chlorite that are forming from those original minerals. So that does happen in the formation of epidote and chlorite. Titanite, muscovite, fengite, and biotite also may form as accessory minerals. We'll show more examples of thin sections and pictures of these later. And oligoclase and andesine may coexist with epidote at low pressures, and these are plagioclase intermediates. So somewhere in between the really sodium-rich albite and the really calcium-rich anorthite are these oligoclase and andesine minerals, and they may show up as well. And at high pressure, low temperature, pumpellyite, which is one of the minerals that defines the P&P facies, that's even lower temperature and pressure, might be present in this Greenschist facies. And we can see a pumpellyite metabasite in the top corner here, but some consider the assemblage of pumpellyite and actinolite to be its own facies, because the P&P facies is, as we'll see later, defined by the absence of actinolite, whereas the Greenschist facies has actinolite, but some think that if actinolite and pumpellyite are present, then it's its own, like in between P&P and Greenschist facies. But I'll show more about that low temp facies and stuff later. Next, we have the Blueschist facies, which, as we can see on this graph, is higher in pressure than the Greenschist facies, but a little bit lower in temperature in some areas and the same in temperature in other areas, but where it's the same in temperature, it's much higher in pressure. And in the Blueschist facies, it's basically defined by looking blue because of minerals like sodic amphiboles that have a bluish purple tint to them, like crossite and glaucophane. This occurs because with increasing pressure, actinolite disappears and crossite appears. And eventually, with even higher pressure, glaucophane takes over. And crossite has a deeper purplish color in thin section, and glaucophane has a lavender blue color in thin section. And these are plain polarized light and cross polarized light. They're different colors. Remember that cross polarized light brings interference colors into play. But the plain polarized light, apparently crossite is a deep purple color, which I think it's more of a deep blue, but I don't know. I'm sure I haven't seen all the samples of crossite, but the pictures I've seen look more deep blue, and the glaucophane looks more light blue rather than lavender blue. But, here's the pictures. You can make up your own mind, or, find your own rocks that have more purple color. Epidote can also be present in these blueschists. Actually, in the previous page, we had this picture at the bottom. That's cross polars of this middle picture here. And you can see there's some blocky, colorful bits here. And I think that is epidote. And you have epidote blueschist at high temperature, low pressure. And we can see more epidote in this part. You can see it's kind of blocky and clear under plain polarized light, and then it's blocky and colorful under cross polarized light. And the glaucophane is more platy and blue under plain polars, and then again platy and all sorts of colors under cross polarized light. And then lawsonite, or calcium aluminum silicate, can also be present in blueschists, and that's characteristic of high pressure, low temperature. So epidote, high temperature, low pressure in the blueschist facies. So high temperature, low pressure would be kind of like this upper right corner of the blueschist facies, but could be really along any part of this right side of the blueschist facies. And then high pressure, where the lawsonite blueschist would be down at the bottom, and low temperature would be to the left. So down to the bottom left of the blueschist region on this graph would be the lawsonite blueschists. facies. At the highest pressure, though, at the very bottom of that blueschist region, we have the pyroxene mineral jadeite with its formula here that forms from albite, the sodium-rich plagioclase mineral. And that's the beginning of the transition to the eclogite facies, which is the really high pressure facies at the bottom of this graph. But we'll talk about that facies after a couple of other facies. Potentially present in this blueschist facies among these other major minerals are pompelionite, again, almandine garnet, as we can see up here in this blueschist and in the thin section to the bottom, and then rutile, which I have an example thin section picture of later, aragonite, and stilnomelane. And I'm still not sure if I'm pronouncing this mineral right, but I don't know. If you know and I'm wrong, then let me know in the comments. Here's a picture in thin section in plain polarized. It's this brown kind of radial-ish crystal here that's platy and stuff, and in cross polarized light, here it is. I think the black and white stuff associated with it might be chlorite. This is an example of a stilnomelane blueschist, but there's also, I found an example of a stilnomelane greenschist. Now, my book didn't say that stilnomelane is, a possible accessory mineral in the greenschist facies, but here it is. So it probably can also occur in greenschist, and greenschist and blueschist facies are right next to each other in some points, so maybe there's some crossover there. And this, apparently, according to where I found it, is defined as a stilnomelane greenschist. Next, we have the Amphibolite Facies at higher temperature and higher pressure than greenschist, but around the same to maybe lower pressures than the blueschist, but much higher temperatures than the blueschist. And in the Amphibolite Facies, and what defines the Amphibolite Facies, we have the presence of hornblende, which is an amphibole mineral. And with increasing temperature from the green and blueschist facies, the actinolite in the greenschist facies and glaucophane from the blueschist facies convert to hornblende. The increased temperature also stabilizes calcium in plagioclase rather than just having pure sodium plagioclase, and it causes the disappearance of epidote. And those amphibolites that were metamorphosed from a more calcic protolith may contain diopside, which I'll show in a minute as well. And then those that came from a less calcic protolith may contain chlorite, garnet, or cummingtonite. Hornblende pleochroism, which is something I talk about in my optical mineralogy #1 video, and I'll link it up here to the top right if you want to check it out. But it's pleochroism, which is like its color under plain polarized light and how it changes color as you rotate the stage, is dependent on its relative amount of ferric iron or oxidized iron 3+ and titanium oxide. And since these components increase with increasing temperature, that indicates the pressure and temperature conditions of the metamorphism, or at least the temperature conditions. And so hornblende with a more olive brown color in plain polarized light, as we can see over here, represents a high temperature amphibolite, whereas hornblende with more pure green rather than an olive brown color represents a lower temperature amphibolite. And then hornblende with a bluish green tint rather than just green or olive brown represents high pressure, low temperature. And if you look at where the high pressure, low temperature would be in the amphibolite region, it's really close to the blueschist facies, or where it would be next to the blueschist facies. And so some of the blue tint may be due to more sodic amphiboles present. But in addition to hornblende pleochroism, or color under plain polarized light, epidote and garnet also can indicate metamorphic conditions. For example, in low pressure amphibolites, epidote disappears before hornblende forms, whereas in high pressure amphibolites, epidote can survive with the hornblende, and these are called epidote amphibolites. So we can see over here some colorful blocky stuff. I took this cross-polarized picture of one of our samples in the lab when I took this class, but I didn't take a plain polarized light picture, or I don't have one, so I can't really tell if there's hornblende, but I labeled this as amphibolite, so I think there should be if I went back and looked. And assuming this is an amphibolite, all these blocky things would be epidote that are colorful and blocky. And then there's garnet here because at high pressures, anorthite, calcium-rich plagioclase, reacts to grossular, which is a calcium-rich garnet. And so this can form garnet porphyroblasts in the amphibolites. And when garnet is rimmed by plagioclase, that could represent that the rock underwent decompression after metamorphism, and the grossular reacted back to plagioclase, because remember, it's at high pressure where the grossular forms, and maybe if it's decompressing and it's lowering in pressure, it reacts back to plagioclase. And then just for some extra examples, I went onto the internets because this here in the middle is my sample, and I wanted to make sure I gave you, what the internet says is epidote amphibole. And so I found, and I'll link the website down below, but one of the websites did have a whole section about epidote amphibolites. And this is the plain polarized and the cross polarized light pictures that they showed for that. To me, it seems these are more plage rich. I don't see any garnets in here, but I'd have to move around the thin section and see. But there does seem to be some blocky, colorful epidotes in here. Definitely the green stuff in plain polarized light is hornblende. Next, we have the Granulite Facies, which over here you can see is the highest temperature metamorphic facies. And this is defined by the breakdown of hornblende as we get to those really high temperatures past the Amphibolite Facies. And it breaks down into orthopyroxene and augite, which augite is just a clinopyroxene. So you'll see me use augite and clinopyroxene kind of interchangeably here, just because I'm using it the way my book did and they kind of used it interchangeably. But anyway, the amphiboles just basically convert to pyroxenes during this transition from amphibolite to granulite facies. And low pressure granulite has a assemblage, a mineral assemblage of orthopyroxene, clinopyroxene, or augite, and plagioclase, plus or minus hornblende as it continues to break down. In some, olivine may be present. And now we might be thinking, well, that sounds a lot like gabbro, the composition of gabbro, or basalt, which is just fine grained gabbro. But because this has the same basic composition as gabbro, we have to turn to texture to really distinguish granulites from a mafic protolith. And the way we can do this is looking at tabular grains from the primary igneous texture. If there are tabular or elongated plagioclase minerals, and these are a lot of times called plagioclase laths. And if there are laths in here, it's not metamorphosed, or at least maybe it is, but low temp and low pressure, it wasn't very deformed to deform the tabular texture here. But this is very indicative of original primary igneous texture and therefore an igneous rock. Now, in these examples, the diopside, or what I think is diopside, or some sort of pyroxene, the colorful stuff, and these igneous gabbros here, these aren't blocky like they typically would be if they had formed euhedrally, which is like with well-defined crystal faces, but it seems they might have formed in the interstitial spaces of the plagioclase, ground mass, potentially later on in the crystallization of that melt. And so that caused them to be more anhedral, or with poorly defined crystal faces, than they would be if they had formed earlier in the crystallization and formed euhedral, blocky, well-defined crystal face pyroxenes, but they seem to have been, more blobby, which is fine because we still know that it's primary igneous texture because of the plagioclase tabular texture. Whereas in granulites, the texture is more granular. So it's pretty, it makes sense because that's its name. And this is called, in metamorphic petrology, Granofeld's texture. And so we can tell that, the plagioclase in this rock is all kind of a blocky microcrystalline matrix type of thing rather than lathy. However, a little bit of tabular lathy like plagioclase texture can be preserved in metamorphic rocks, and I'll show an example of that later, but it's still pretty obvious that it's been metamorphosed, and I'll show you why later. And here's just another example of where we've got plagioclase, pyroxene, and quartz in a granulite rock. And here's a hand sample example. And in the hand sample, we can see some garnets. And that's because at high pressure, granulite can contain garnet. At even higher pressure, orthopyroxene reacts to augite and garnet, or clinopyroxene and garnet, and that makes an assemblage of garnet, clinopyroxene, and plagioclase. And with increasing pressure, because the calcium component is going into grossular garnet, you have the plagioclase becoming progressively more sodium rich. And then that sodium-rich plage, or the albite, goes into jadeite, which is a pyroxene, which then dissolves into clinopyroxene. And so we're all coming back to augite here. And plage, it gets eventually completely consumed and converted all the way to clinopyroxene, or augite. And the disappearance of plagioclase marks the transition into eclogite, or the eclogite facies at really high pressures here. And here's an example of eclogite that I gave in my classifications or identification metamorphic mineral thin section video. And here we can see we've got the garnets, the black isotropic class, we've got quartz, the black and white speckly class, but I called the blocky stuff epidote, but now that I've read about how these transitions work, I think it's augite or clinopyroxene. So sorry for that misinterpretation there. And with that, we have the eclogite facies, which contains dominantly garnet and amphibole. And amphibole is just sodium-rich augite, which makes sense because we just talked about how sodium-rich plage converts all the way to augite. So all that sodium is making this augite really sodium-rich. And then we can see a picture of amphibole here. Down in the middle, we also see another picture of eclogite that I showed in that thin section identification video. And I didn't mention this in that video because I didn't think about it. But now that I think about it, I think the rims of these garnet class here, which are all black because they're isotropic under thin section, the rims are kind of this, pinkish orangish interference colors under thin section, which is very typical of things like augite or amphibole. And so I'm thinking maybe they're rimmed by augite because, like we talked about in the amphibolite section, the garnets can be rimmed with plagioclase if undergoing decompression after they underwent high pressures. And that plagioclase that then rims the garnet, if pressure is increased again, might transition into augite. So it would be interesting to see, but I could see that happening in the environment. If you have a plate moving and then there's really increasing pressure, and then maybe it stops moving so fast and it kind of decompresses, and then it starts again and compresses again. I don't know. Other common minerals in eclogite, though, are kyanite, phengite, and rutile. And over here in this thin section, we can see example of rutile and cross-polarized light. And in terms of environments where eclogite can form, because again, it is really, really high pressure, but it goes over quite a range of temperatures from low to high. So the types of environments where that would be possible would be, for example, low temperature subduction zones where you have a really cold slab maybe subducting, but also can be high temperature continent-continent collisions. The last couple facies we'll talk about include the more low temp facies, like the zeolite facies, for example. This facies is defined by the presence of zeolite, so it's well named. And high temperature zeolite, so on the high end of the zeolite facies, would be the mineral lawsonite, but also calcite, which we can see some of blocky crystals of in this thin section here, along with quartz and some mica minerals over here. The calcite has cleavage or twinning under thin section that is really distinctive, and you can't really see it that well in this thin section, but if you see my metamorphism of carbonates video, which I don't think is out by the time this one comes out, but should be out right after it, that one shows a lot of examples of calcite under thin section, especially in marbles, and so I'll show those examples in that. But then you also have albite, which is that really sodium-rich plagioclase in the zeolite facies, or the possibility of albite in the zeolite facies. And in this example, the albite retains a little bit of its tabular structure. Then we also have quartz and chlorite that are common or potential in the zeolite facies. Also epidote, which I accidentally wrote eclogite here. Sorry, that's supposed to say epidote, not eclogite. Also prehnite can be present in the zeolite facies, and pompelliite, which we've talked about, and those are what the P and P facies stand for. It's the pompelliite prehnite or prehnite pompelliite, I don't know, that facies. And that's the next one we'll talk about, but those can also occur in the zeolite facies. Speaking of PNP, or the prehnite pompelliite facies, this is basically when lawsonite disappears, or that high temp zeolite disappears, and the assemblage becomes chlorite, epidote, and quartz, with obviously prehnite and pompelliite. And we can see the transition from zeolite to PNP is just an increase in pressure and temperature. And this facies is distinguished from the Greenschist facies by the absence of actinolite. Sometimes, however, lawsonite, that high temperature zeolite, may survive into the PNP facies, but will not occur with prehnite or pompelliite. And then the transition to the Greenschist facies is marked by the appearance of actinolite and disappearance, along with the appearance of actinolite, the disappearance of prehnite and pompelliite. And I'm also sorry if I'm saying pompelliite wrong. It might be pompelite instead of eite, but I don't know. I'm just saying it how it's spelled. Then we have a whole separate technical facies that's not even listed on the graph here that some people stuff into the zeolite or PNP facies, or just that region of low temp metamorphism, but it's the assemblage where you have lawsonite, albite, and chlorite. Lawsonite can be seen in these blocky, colorful crystals over here, and this assemblage is basically, in terms of facies, a high pressure equivalent to the zeolite facies. So if we go back, we can see just between the blueschist and the zeolite facies, there's kind of blank space. That's where that might happen. And it could happen if you have subduction of a cold slab, produce low temperature, but high-ish pressure conditions. But obviously you're still in the zone of relatively low pressures, because we're talking about, relative. Every time I say high temp or low temp or high pressure, low pressure, I'm talking within the zone or region that we're talking about at that point. So high temperature for the Amphibolite Facies is really different than high temperature for the Zeolite Facies, And for the next few slides, I just want to finish up by kind of summarizing what we've talked about in terms of different minerals that show up in different facies. For this one, basically we have ferromagnesian minerals and calcium aluminum silicates that show up at various different facies. And so I'm just going to go through and basically facies by facies say which minerals are common in those facies. And so zeolite facies, the very low temp and pressure facies, the very first one after diagenesis basically, can have its ferromagnesium content tied up in chlorite and its calcium aluminum silicate content tied up in zeolites and potentially prehnite and epidote. And in the PNP or prehnite pompelliite facies, we have chlorite again for the ferromagnesian minerals, and for the calcium aluminum silicates, there's epidote, pompelliite, and prehnite. And then lawsonite, albite, and chlorite is that assemblage that may represent its own facies between the zeolite and blueschist facies. And this has chlorite again and lawsonite as its calcium aluminum silicate. And then the Greenschist Facies is characterized by its ferromagnesian content being an actinolite, and epidote and Plagioclase being the calcium aluminum silicate content. And then the Blueschist Facies is characterized with sodic, amphibole, chlorite, and almandine garnet for its ferromagnesian minerals, and then epidote and lawsonite for its calcium aluminum silicates. And then amphibolites have hornblende and potentially garnet at higher pressures for ferromagnesian minerals, and plagioclase and potentially epidote for their calcium aluminum silicates. And then granulites contain orthopyroxene and clinopyroxene or augite, and potentially garnets for ferromagnesian content, and plagioclase for calcium aluminum silicates. And then the eclogite or very high pressure facies is amphibole or that sodium rich augite, and almandine garnet for ferromagnesian content, and then grossular garnet for the calcium aluminum content. And now the coolest table of them all that really ties it all together is this facies by facies mineral transition table, which I think when I saw that in my book, I was like, this is perfect to kind of bring it all together and make it all make sense. So here we have the original minerals. And so we're going to go mineral by mineral, facies by facies, what it turns into. And the original orthopyroxene and augite in the zeolite facies goes to chlorite. The olivine content goes into chlorite as well. The anorthite or the calcium-rich plage goes to lawsonite in the zeolite facies. And remember, that is a high temperature zeolite mineral. And then the albite or sodium-rich plage stays albite for the most part. And then the other accessory minerals that might be present due to the formation of some of these minerals is quartz and calcite. And then in the PNP PP Facies or Prenite Pompelliite Facies. We have some of the chlorite contributing to Pompelliite. We have other chlorite staying chlorite. We have the lawsonite going to both Prenite and epidote. And then the Albite stays Albite or sodium plage. And the quartz and calcite accessory minerals stay and potentially become more abundant depending on the chemistry involved with the formation of those minerals. And then for the Greenschist Facies, we have the disappearance of Pompelliite and the appearance of actinolite. We have chlorite staying chlorite, we have epidote staying epidote, we have albite staying albite, and we have quartz is present instead of calcite at that point for accessory minerals. And then in the Amphibolite Facies, we have hornblende from the actinolite and chlorite content. We have Plagioclase from the epidote and albite content. And then you have potentially quartz and garnet at higher pressures. And that is all there is for the Amphibolite Facies assemblage. And then in the Granulite Facies, we have hornblende going to both orthopyroxene and augite, as well as olivine at very high temperatures. And then Plagioclase stays Plagioclase, and quartz and garnet remain depending on the pressure conditions. And then moving backwards to the Greenschist Facies so that we can go to the Blueschist Facies now, which remember is at that lower temperature, higher pressure into the Greenschist Facies. So first we went through the center of that graph, if you remember, is Greenschist, Amphibolite, Granulite. Well, now we're going Blueschist, then Eclogite, so higher pressure, low temperature. And the Blueschist Facies takes the Greenschist actinolite and puts it into sodic amphibole, and that's purplish to more lavender blue as you get higher in pressure. And the albite content way down here, or the sodium plage, also contributes to the sodic amphibole to make it more sodic or sodium rich. And then chlorite contributes to garnet. Epidote goes to both epidote and lawsonite. And then albite can also contribute to not only sodic amphibole, but also sodic pyroxene. And then you still have plus or minus accessory quartz. And the last facies, eclogite, has sodic amphibole converting to sodic pyroxenes, epidote staying epidote, garnet staying garnet, and potentially quartz, kyanite, and muscovite also present. If you want to check out the related videos to this one, you can check out my metamorphism of politic rocks or shales in the upper left corner, and the identification practice thin section hand sample video in the middle here. And then you can also check out the Metamorphised Protoliths playlist once it pops up on the screen. All of these should pop up at any moment now. And then you can also check out my reference, which is linked in my description down below, and it's The Essentials of Igneous and Metamorphic Petrology by Ronald and Carol Frost. And with that, guys, thank you so much for watching, and I will see you guys next time. Bye. Wait, she's lying. Her face is totally like in the blanket. I don't know.